fastball. It doesn't diffract. It probably would help the pitcher if it did diffract, and when it underwent interference, it'd probably fool a batter really well. However, the wavelength is just too small to be demonstrated. Well, let's look at something smaller, an electron. An electron has a mass of 9.1 times 10 to the minus 31 kilograms. Let's give it some intermediate speed, 6 times 10 to the 6 meters per second, which is not terribly fast, since speed of light is 3 times 10 to the 8th. Well, what do we get there? There we get that the wavelength is about 1.2 times 10 to the minus 10th meters. And that is on the order of a magnitude of the size of the atom. Note that. What does that tell us? Well, first of all, the electron has a much bigger wavelength, or longer wavelength, than a baseball, fastball. But since the spacing between the atoms is 10 to the minus 10th meters on the order of that, we can demonstrate the wave nature of electrons. Because now we can come up with slits. If we do it between atoms, we can send electrons through these slits and see if we can observe wave behavior. Well, this was actually observed, and how it was done was electrons were shot through a metal, and they were observed to undergo interference. There's a schematic of what happened. We shoot a beam of electrons coming in, and we put a phosphorus screen where they hit, and what this diagram shows us is that a lot of the electrons go straight through to the central peak, but there are rings that form. There are preferred directions at which the electron will scatter, and that is due to constructive interference. The dark rings are due to destructive interference, and it's because of the wave nature of the electron. This would not happen if electrons were just simply treated as particles. This cannot happen. It can only come about due to the wave nature, and that should be clear. So what we see here is electrons, which we often think of as particles, can also be thought of as waves. Now, the experiment confirmed de Broglie's idea that the arrangement of the scattered peaks matched perfectly if the electrons are interpreted as waves with the de Broglie wavelength. So it's dependent upon their momentum. The thing to notice here is that each electron hits separately on the screen as we observe it. We only see one hit at a time. However, where the hit is dependent upon the wave nature. So it's not a continuous pattern. This is an accumulation of several hits of electrons. It was later observed that other small particles, protons, neutrons, have wave properties as well. And when you get to large particles, it gets very hard to demonstrate it because the wavelength gets so small. So what we've seen is that the wave-particle duality extends from light to all the matter, everything. Everything needs to be viewed in this dual way, depending on how we look at it. So everything has wave and particle properties depending upon the experiment. Well, this leads us to ask the question, we're getting into philosophy now, what is an electron? Now, we've always said that it's some kind of particle that we've represented by a little ball, and it moves around and it has a negative charge. And we had this view of the atom in this sense, where we had protons and neutrons in the nucleus, and we had these electrons buzzing around outside. Is this a correct picture of the reality? No, it's not. No, it is not a good picture of the atom, because the fact that the electrons must be treated as waves, and they are not hard little spheres that bounce around. They're not that simple. Is it a wave? Well, not always. It does exhibit wave properties, but the measurements show point-like properties. Now, to examine here, we see the accumulation of these electrons adding up, and in the end, they form this interference pattern, but each electron is a separate, distinct particle. Each hit is one electron, but they do interfere with each other to form this pattern. So that is kind of bizarre. So at this time, it was starting to become clear that we simply cannot make a picture which completely describes the reality of an electron, or a photon or proton, or anything that's on a small scale. We can't just say it's a particle. We can't draw a picture of a ball and say that is an electron. That is not an accurate description of what an electron is. We must take account of both the wave nature, which we can't really draw, well, we could, but it'd be very difficult, and also the particle properties, which we can do. So this is the important philosophical point, which questions our notions of reality. We can't just picture it as a simple ball that's moving around. We'll come back to this when we talk about the full theory of quantum mechanics, where we amplify on this point that we can't really describe the reality of the electron, because it does require the full theory in order to begin to understand this viewpoint that we can't describe the reality. you could say, well, it always exists, it's always somewhere. Well, quantum mechanics says that is difficult to pin down, and it doesn't always exist in the way that you think it exists. That sounds kind of mysterious, and it is mysterious, but it is physics, and we'll get to it when we talk about the full theory.